Good morning. Today we're looking at local linearity, section 3 out of chapter 3, rate of change in derivatives, out of business calculus with Excel. Since most nice functions look like a straight line when we zoom in it far enough, that was the idea of derivatives, we often want to use a line to approximate a function near a point. If our function is discrete, we only have values at whole number inputs, we use the marginal rate as the slope of our line. So if I know that the marginal rate is 7, producing one more product, I go up by 7, I'm going to do point slope form where 7 is my slope. If we have a formula for f of x, we can use the derivative for the linear approximation. So we take the derivative, that's the limit of the difference quotient, and use that as my point slope form. As is normal practice, I'll follow the structure of the text but not do the same examples. Videos of text examples are attached to the text. So we're going to start with the discrete case, and I'll want to look at the formulas underneath. If we show the formulas, I have a starting point and I'm going up by 1, and what I know is that at 100, f of x is 112. At 101, it's 117. So my marginal rate is the difference of those two, which is going to be 5, and f of x0 is 112, x0 is 100. If I want my straight line, my linear approximation, point slope form, I'm going to use the slope, the marginal function, times the distance I've gotten from my base point plus the y value at my base point. And so if what I have is that I went from 112 to 115, my approximation is we're going to go up by 5 each time, and that gives me a linear approximation to this function based on the marginal value in these first 2 points. If I want to turn to the continuous value or a value with a formula, I can set up a template. Again, I want to look at my formulas, and I'm just setting up a template where these 2 rows are going to find the derivative. I have x plus 0.001, x minus 0.001. I'm going to put f of x in. I'll drag over to get that evaluated at x plus 0.001 and x minus 0.001. The top is going to be the difference of the 2 values, and the bottom is going to be 0.002, and the derivative is just going to be the quotient of those. So my linear function is going to be my base y plus my derivative times the distance my x moves. And this is a template that I can copy and use with different functions. As a matter of fact, I've done that. So the first function we want to look at is log base 10, and look at it in the area around 1,000. I've set it up to do the derivative. So if I look at my formulas, I have x plus 0.01, x minus 0.01, log base 10 is the formula. It's on A6 at x, it's on B6 at x plus 0.01, C6 at x minus 0.01. I have a top and a bottom. I take the derivative and it gives me a slope. What's worthwhile noting is if I'm looking at points around there, so I'd like to look at my function. I have f and the linear approximation to it. I've seen what happens at the 2 points that are closest. I'd like to look at what happens if I extend that down for some distance and look at a region around it. And we'll see this is one of those functions that the difference between the actual value and the linear approximation is not that much. And so once we have the first point, rather than checking my common log function, I'm simply going to use the linear approximation, and that's giving me a value that's close enough. It's worth noting that if I get further away, like at 1200, errors start to creep in and they start to be bigger. And so by the time I got to 10,000, my error becomes substantial. So the linear approximation is only good in a close region, but it does work there. If I want to look at a second function, I'm going to look at computing interest. So my function is 1,000 times 1.06 to the x, and I'm looking at a route around 10 years. At 10 years, my output is $1,790. I have the familiar template that I've used for computing the derivative at 10, and that's 104.35. And then I set it up to compute the values of both the function and the linear approximation. Looking at my formulas, we see that my linear approximation is the initial value of y plus the derivative times the initial times the distance you are from the initial value of x. That's my general setup. It's a pretty good approximation for an area around there as I'm close to 10 years. The caution, however, is as I move farther away, that if I move to 20 years away, my approximation is not that good. Again, this is a curving function, and as long as we're close enough that it looks like a straight line, we can use it as an approximation. This is the whole idea of linear approximation. If we know the value of the function and the derivative of the point, we can approximate the value of the function close by. Thank you.